Okay, so the record is now on. Let us see more sine wave problem. That one was quite a good introduction to sine wave with the real numbers. Okay, now I'm going to show you some cases where, you know, it will demonstrate why we need to use the psi in terms of delta. So let us take a look at this frame. In a typical frame, not like a good straight line at all, but you know, the columns or the legs, they are not equal, of equal length. This guy is going to be pushed by the load P somewhere with the distance, say, A from the support. Okay, now we know because of the assumption that the sway is going to be equal. So the delta is going to be equal. Notice that now the point is this is going to be equal, but because the these two legs, they are not equal anymore. So that would mean you are going to have different psi term. Right? This psi will not be equal to that psi because these two legs, they travel with the same distance delta. So therefore, with the legs are not equal, but they travel with the same delta, in the end, that would mean your psi will be different. So if we don't write the unknown in terms of delta, you will end up with two psis in your equation. And with two psis, it would mean that we run out of equations to solve it. So it's only natural and necessary that we convert the psi term into the delta to reduce the unknown, because another equation that we could actually use is the relationship of the psi, but we use it in terms of delta. Okay, so from here, I think let's give it some name, because I already used pink. No, that's fine. It's green here. A, B, C, and D. Now we know our unknowns are theta B, theta C, and then delta. Okay, and we are going to use the sigma MB equal to 0, like the previous example, sigma MC equal to 0, and then sigma Fx equal to 0. Now, keep in mind that this guy from the delta here, now you will know that the psi of member AB will be equal to delta divided by the length of member AB. So is it safe for me to write like that? And psi, okay, psi of member CD now, it's going to be equal to delta, but divided by the length CD. See, we have psi terms on member AB and CD, but not on member BC. Keep that in mind. But now when you consider your sigma Fx, again, it is for these two basic equations, we're not gonna spend time on it, okay? So let us focus on sigma Fx equal to 0. Or you can say HA plus H, that's not A. HA plus HD plus P equal to 0. But this time, you guys are going to have the force on member AB. And because, you know, you should always trust what we call free body diagram. Okay, so that means your equation will be derived from the free body diagram. So now when you have a free body diagram like this, you better include P in your equation, correct? So now when you try to write HA, you better have this. Force due to P, and then force due to the end moment. And this time it is clockwise BA, and then MAB. Okay, so now you can say that this is HA, right? We don't really want to know how much this is, because in the end we want the sigma fx equal to 0 of the support reactions. So you can take the moment here, and therefore in this case HA here, it will be equal to P, if you believe in free body diagram, that's length AB minus A, right? Over length AB. Okay, and then this will be equal. Be mindful of the direction of the force as well, because right here you're gonna have the force in this direction. Okay, and let me call this HA prime. HA prime is gonna be MBA plus MAB over the length AB. Hang on a minute. So here we go. See, it's the same as we did before, but you know, with the presence of the force now on the member as well. So you have to include that in your free body diagram. Simple as that. Okay. And the rest for this guy, we have MCD and MDC. So you have HD equal to just maybe it's in this direction. Okay, MCD plus MDC over the length of member CD. Okay, and there you have it. You can construct your sigma fx equal to 0 equation. Okay, is there any question on this case?
Why we have the MAB clockwise?
Oh, because remember that we use clockwise positive for the sign convention. So I prefer to write things in clockwise, that's all. Even though it may be in counterclockwise, okay? It just, it could probably help you better in terms of managing the sign convention and stuff. Because remember that your slope deflection equation is based on the clockwise positive sign convention, okay? All right. Now, let's take a look at another case if we don't have any more questions. Do we? Or we don't? We do? We don't? Now, it's going to be more fun because when we know we can use this slope deflection to handle a more complicated structure, why don't we add another floor to it? Like that. Okay. So now, how many unknowns are we gonna have? Let me do the most difficult part for you, that is giving it some name. Okay. A, B, C, D, E, and F. You may think this is not gonna sway, so let's put some load on it. P. So folks, what are the unknowns? What are the unknowns? Okay, you guys don't have idea. So let me do the difficult part for you. It's gonna be zeta B theta C, theta D, and theta E. So now you do the easy part. What are they?
Delta D.
Delta, right? How do you call that? Let's
Delta D.
call it like this. Delta 1. How many delta are we gonna have?
2.
2. Good.
2 delta.
Delta 1 and delta 2. So you know, this guy is gonna sway like this. It's a fixed support, so it's just gonna go to the side. Okay. Now let's call that delta 1, shall we? Now it's just gonna keep going. Now this is going to be the delta 2 should be the one that you count, you know, from we left off here. So that will be your delta 2. Knowing that the total deflection would be delta 1 plus delta 2. Okay. So yeah, we have 6 unknowns to contend with. But now, yep, we know now that we are going to need 6 equilibrium equations to solve this structure. So I can say equilibrium equations here that we are going to have will be sigma mb equal to 0, sigma mc equal to 0, sigma md equal to 0, and sigma me equal to 0. Notice that these 4 moment equations are for those 4 rotations, right? Now you have 2 deltas. It means that you are going to need sigma fx equal to 0. But then, because we now have 2 delta, so I think we are going to need sigma fx equal to 0 twice. Okay. And how are we going to do it? Well, we are going to do it by cutting the free body diagram, right? Here, perhaps. And are you going to have now that this portion, right? P, and then it's not going to be nice to write this as a reaction anymore. So let's call this HB. And that is going to be HE. And that's P. Okay. Now your equation will become HB plus HE minus P equal to 0. And again, you will obtain your HB from what? Okay, so we stick with the same sign convention. So this is clockwise. And that gives us the, actually, you know, from the nature of the structure, it's like that. So, you know, when you write this equation, you be mindful of the sign, okay? So that will give you the HB in that direction. And here it is going to be equal to, that becomes MCB, that is MBC. So it is MBC plus MCB divided by the length of member BC. And you can say that you can do likewise for HE. Let me just do it for you. that we have a complete picture. Here is MDE. That is MED, and that should give us the equation that will show you HE, but it's in that direction. Okay. So HE is equal to that's going to be MDE plus MED divided by the length of member DE. And in the end, you can put things back to that. So account for the direction of the force as well. You know, let's say if you say P equal to negative, it means going to the right. This is going to the right, so it all becomes negative. You know, and things will work out in the end for the sign. Now it's the next free body diagram. So you guys should be able to guess now that the next free body diagram is going to be this one, right? The entire structure, of course. So you have P here, you have P here, and now you are going to have the HA and then the HF. So the equation here is going to be HA plus HF equal plus maybe minus 2P equal to 0. Okay, and in similar fashion, we go to the free body diagram of member AB, and you see that you now have MAB, MBA, but then again, this clockwise will give you the HA in that direction. You need to manage that. And this is member EF, where you have MEF and MFE, which will give you again the HF in that direction. Okay, and likewise, we can now have the HA equal to MAB plus MBA divided by the length AB, and HF similarly MEF plus MFE divided by EF, the length of EF. Okay, it's getting longer a little bit. Okay, another one that is very difficult to draw, but I would like to give you this experience is that when you have, let's say, can I find the easier one than this one? Maybe this one. So we're going to use this in the let's do the sketch. Okay, more fun. But let's say I should use the blue one. This. Now you see the frame didn't have the vertical member anymore. Because some of you would really like to add the side term to the horizontal member. In this case, you can, you know, this. Okay, let's push it down with the load. Now you look at this member. It's not symmetric. It doesn't have any lateral load, but it will have side sway because it's not symmetric. Because of the unequal legs like this, so it's gonna go. Maybe, you know, it's just gonna go to the side like that. That means you probably see that I like this color. this is a fixed support, right? So with zero rotations, but this guy could just go down like this. See? And that becomes your psi term. If I should, difficult to draw. Okay. If I should, you know, connect these. So that becomes my psi term, right? But then when this guy, let's say we assume that the whole thing goes to the left. That means the left column, let's call it a column, okay? We will go to the left as well. And because we say that the axial deformation is negligible, so if I say this guy goes with delta, it means that this joint must move with delta as well. Correct? But in order to move delta to the left, it has to go up, right? From zero rotation, just have to go up. And it has to be 90 degrees here, right? That has to be 90 degrees because it's a rigid joint. Okay, and when I connect this, one. Okay, so you know it's like a wind, you know, windshield with the wiper. That your wiper will go like this, right? So one go, if both of them go in the same direction, one moves up and another moves down. So with that, we have a delta. So this side will not be equal to that one. So I can call this AB, maybe, and I can call that CD. And then you see that this time, member BC on top, it will move up and down, see? Oh. Okay. So that will become psi BC. A case like this is quite a killer, right? Because please notice that I have the delta here as the unknown. If I go ahead and use the psi, you know, you guys and I are going to end up with 3 unknowns. But in fact, what we should do is we will use the relationship to turn these 3 unknowns into 1 in terms of delta. But that means you need to find a way to convert this delta, which is the horizontal displacement, into this distance. This distance is perpendicular to the member. And then use this distance to calculate the psi to maintain just 1 unknown, because in the end, this guy has 3 unknowns. So the unknowns, let's give it some name. A, B, C, and D. So the unknowns are in fact zeta B, zeta C, and then delta. And you guys are going to use the, of course, sigma MB equal to 0, sigma MC equal to 0, and then sigma fx equal to 0. But sigma fx is going to be quite, you know, take some time to obtain it. Okay, I have the example for this one, but perhaps we're not going to use it. Another interesting case is this, you know, when I used to give this, let's say it's very fun. When you look at this structure, for example, hinge and roller. So that's determinate structure, right? Now I used to say solve this by using slope deflection equation. So that means you're going to have to consider the sideways problem, right? And now how many unknowns you're going to have? This is a one time, you know, a very rare occasion where the slope, where the displacement method will become more difficult than the typical method, because it's a determinate structure. Let's say if I push this maybe like that, your unknowns are going to be, you know, let's say this is A, B, and C. Your unknown is going to be theta A, theta C, and then delta, right? So to make matters worse, if you don't use the modification, you have to solve this too. But if you use modification, they're gone too, right? So it will be fun how things will turn out. Oops, I'm sorry. Actually, it's theta B. It's 4 unknown, right? 4 unknowns. So it's a theta B and then delta. Okay, and this guy is gonna sway because this one will come down, right? With that, that's your delta. And then because of the fact that this is roller, so this guy will be delta. And that guy will be delta as well. Okay. So this time, both member AB and BC will have side term. Quite a mean problem to solve by displacement method, really. But let's say I also used to give something like this. And this becomes easier because let's say you have member A, B, C. Member BC will not sway now, but member AB will, because of the presence of the roller. So this guy is going to go like this. This is the wrong curve. Excuse me. This is probably the better one. Okay. This guy is going to go like this too. So okay. See if you understand the matter. It shouldn't be a big problem. Okay, there is another one, but it's pretty difficult to draw. Now, I think I'm going to have to find some time to practice it, because otherwise it will create confusion for you. That's why I don't draw it today, but I can give you a glimpse of it. It's a cable frame. Like that. Say fix and fix. When it wants to go, it's just going to go like that. Equal, maybe not, because of the nature of the cable. So these two doesn't have to be the same anymore. You know, you can have delta 1 here and then delta 2 there, and then, you know, this guy will just go like this and then that. Very difficult to draw. And that's, you know, the distance here becomes the difference between the delta 1 minus delta 2, something like that. Okay. But this is for the sake of demonstration. We're not going to delve into the calculation of these things, just for you to know. Okay. We only need to do exercise enough so that you understand how to use slope deflection. That's all. So that's it for today, I suppose. Any question? Hello? I think I'm gonna spend some time, if I don't forget, try to solve this problem and you know, give the answer to you next time. Not this one. Oh, here, I mean this one. Okay. So is there any question?
Could you back to the last demonstration, please?
This one?
The last one.
This?
Yes. Why it will be like a delta 1 minus delta 2, and how to make sure that delta 1 will be greater than?
No, well, we don't know.
Okay, just to
it just you know, if delta 2 is greater than delta 1, that is going to be negative, and just, you know, move to the opposite side. No big deal. Nobody knows. We have to perform some calculation.
Why we need to subtract together? But I think just
because no, let's say it just the movement on the tip of the cable frame is just going to be the difference between these two displacements.
Oh, okay.
Correct. Let's say if delta 1 is equal to delta 2, that amount is nothing, because they all move together. But because of the nature of the, you know, two members put together like this, it just can go up and down. So that's why delta 1 and delta 2 may not be equal.
Okay, I see. Thank you.
If they're equal, it becomes a straight line, right? Which is not possible.
Yeah, no matter.
Good. Any question? It's time that we have some homework to do for this class. So please expect to have some by tomorrow. Okay. And if there isn't any more, let me stop the